Our next presenter is from Car Biosystems. He is Dan Nelson, Director of Product. He's going to present case studies to illuminate critical process parameter considerations such as shear, separation efficiency, and process speed when developing, when developing separation processes, including primary clarification, cell retention, wash, and concentration. And we're going to learn about tubular bowl centrifugation works, how that works. So thank you. Welcome, Ben.
Thanks for the introduction, Perry. Excited to be here. We're going to be talking about cell separation, as you mentioned in the intro, and how critical process parameters can be tuned for your process goals across a variety of biomanufacturing workflows. And I see that the separation technologies poll question looks like it up. We were going to ask that in just a moment, but we'll tie that in. We're interested in what you've worked with, and we will share the results in just a few slides. So if you could take a minute and check what you've worked with, then we'll come back to that. So a quick note on Car Biosystems. We've been around for a few decades working with developers and manufacturers across a variety of biomanufacturing products. So you can see some of our history here with approved products and even some of the more emerging markets and applications, but a robust history with the team. We launched with and started with stainless steel systems, but in the last 10, 15 years, we've been focused on advancing some single-use products. In the broader context of biomanufacturing, everybody separates. And I kind of look at these two different products these products in two different ways. One, where the cells or the products. Second is where the cells or the factories or they're churning out the valuable product. So there are many unique separation needs throughout these different modalities, and there are many questions, or there are many technologies to choose from based off of what it is that you might be doing. And so based off of what application, the specific application that you're running or primary separation activity will depend on a few things in terms of your goals. So when it comes to primary clarification, we're typically working with CHO or HEC cell lines where it's important to remove all of the cell debris, the waste, and pass on the purified product for further purification. Second is when we look at the cell as the product. So this is when we're harvesting, washing, concentrating. And typically we're looking at the stem cell line. So this is more in the cell therapy industry or in cultivated meat. And then last, another way that I look at primary separation applications is in cell retention. So the cell isn't necessarily the product, but it's needing to be used for further processing. And so here we're looking at media exchange or perfusion. We're looking at seed train or seed banking. We might even be doing transfection or gene editing. So based off of the different applications, you might be working with a particular cell type. You might have a different product of interest. You've got a unique separation application. And as we work with people in a lot of these different, or in all of these different areas, we hear some of the biggest challenges and common themes as we're working through the development with them. So one of the first ones that we hear is, I'm losing a lot of my products. So I've got bad yields. I want a step increase of my yield. I'm losing it to the filter matrix or something else. Another thing on the efficiency, I want to reduce my downstream burden or impurities. Or I'm spending a lot of time preparing and operating and disposing these consumables and the buffers that are involved. Or I've got a lot of products and a lot of different processing needs or separation steps. So I'm looking for a more versatile or a robust way of handling this and all of my platform needs. And then kind of summarizing all of that, hey, you know, these things, this costs a lot. We're talking about a lot of materials. We're talking about a lot of operator hours. So my team is really busy. What can we do to change this process and really get to the processing goals that we have? So let's take a look at the live results. Miles, there we go. Thank you. All right, so we've got a lot of depth filtration, some centrifugation, disc stack and tubular bowl, a lot of TFF and ATF. So a good mixture here. And this is something that, you know, I think this is something that we would expect, because each one of these separation applications has different needs. So how do we work with our customers to engineer the outcomes? We do that by tuning these critical process parameters based off of their specific characteristics and what those goals are. So we start off by understanding what the input material characteristics are. So what is the cell type? What's the diameter? What's the density? These are things that are going to influence that cell and how it may perform as a product, or what's going to happen to its contents through the separation process. So thinking about primary separation, you know, one example, it would be transfection or gene editing. So this is a case where we are looking to concentrate the cells, exchange the buffer in preparation to receive that gene of interest. So how important is it? How quickly can we get those reagents, the media reagents, away and exchange for the reagent of target and introduce the gene? Shear forces through this, keeping cells healthy and intact during that handling will play a huge role in how they perform after receiving that edit. And then last but not least is processing time. So how long does it spend outside of the bioreactor? This is where we want to balance how fast we can go while still getting that good separation and that recovery. And so we can play with scale and different metrics. And so with tubular bowl centrifugation at the core of our cell processing platform, the critical process parameters that we're looking to control are the G-force, the flow rate, the capacity, the wash. And that's very comparable, right? A lot of you are working with filtration, just a different set of critical process parameters. So let's take a look at with the tubular bowl technology and the reasons why this is becoming increasingly used for a lot of these separation applications, because it has this huge or robust operating range in G-force, 100 Gs up to 4,000, very low flow rates up to high capacity. We can handle down to 100 milliliters all the way up to something greater than 2,000 liter bioreactor. And the wash can be variable in number and volume. So what we've reliably seen across all of these separation activities is greater than 90% cell recovery, greater than 90% turbidity reduction, high viability across the board, excellent washing efficiency, there are continuous and intermittent separation modes, and it's single use and automated, easy to operate. Let's see how it works. Thanks to our team in Clearwater, we have an excellent demo that we typically perform live at trade shows that we'd like to share. Okay, so this is a mock-up demo using dyed beads to illustrate what a typical separation would look like using our benchtop unit. Recipe is programmed, easy push and go. The audio is live, but it's not quiet. When the feed starts, you can see our HMI on the right side showing the bowl is in the act of being filled. So as the feed is continuously fed to the module, the supernatant is being continuously separated. So the supernatant is being pumped out. And here you can see the dark red color. That's the cells that diabetes in this instance collected on the outside of the walls. It's a very small volume, so we process quickly. So it's ready to stop. The food has been processed. And now it's discharging that cell concentrate. Okay. So with the time that I have left, let's look at a few of the results. How's it been working out in the field? So this on the right, top right, this was a study performed to evaluate the effect of flow rate on clarification using our pilot scale system. So you can see the difference in separation efficiencies between 1 and 3 liters. So based off of their particular cell type, the densities, a few other things may be happening. Are you looking to go a little bit faster? So you can see the turbidity reduction difference or the cell removal difference. Are you wanting to go a little bit faster and maybe sacrifice a little bit of removal, or vice versa? You can see on the far right, there's no impact to cell viability. So this is speaking to the inherently low shear nature of tubular bowl centrifugation, which makes it very unique to some of the other technologies available to select from. So regardless of the flow rate in this case, you don't see an impact to cell viability. So you wouldn't be seeing a lot of downstream impurities owing to lysed cells, or we'll talk about retention in just a moment. Another aspect of this, we look at the effect on product yield. So on the bottom right, you can see potential a HEC recovery. So we did an experiment to see how much of the viral recovery we were able to get compared to a benchtop centrifuge. We only lost 3% step yield. So on processing speed, again, going back to the separation efficiency, that's where we look at, again, what volumes are you working with? We can work with scale. We've got lab through GMP. I'll show that in just a minute. But we can shift scales, again, depending on how quickly you may want to process. So that's where capacity becomes another lever that we can do to tune in specifically what your harvest objectives are. So when it comes to cell harvest or cell retention, I think this slide and these experiments, multiple, really speak to how each cell line has unique characteristics, and so we need to make subtle shifts to the processing parameters. And we've gained this working with the number of cell lines. So we can work with you to dial in these critical process parameters and have that separation efficiency, the washing efficiency, and more importantly, we can work with you on various manufacturing strategies, like I've alluded to. Concentration and buffer exchange. You might be preparing to bank your seeds or to bank your cells. You might be doing cell engineering or gene editing, or you might be doing perfusion or seed train. So it's important to know that a solution is flexible and can scale up or down depending on where you're at. So as I've mentioned, we've got single-use and stainless steel options depending on where you're at, what your manufacturing strategies are. And pretty much sums up my presentation. So I'd be happy to answer any questions that you might have.
Thanks, Dan. Really good question from an audience member. they have a DSC at large scale but lack a small scale model. Can the tubular bowl centrifuge be tuned to replicate the conditions of a large scale DSC?
Yeah, I think it all starts with understanding what your characteristics, cell culture characteristics are. And then we work it through. We've got, I see calculators are really popular. We've got a really nice calculator that the process science team has recently launched. And so we'd be happy to chat about what your process may look like based off of changing different variables we can predict or understand what might come out, so that again we can assess options and find the right path forward.
Another audience question, to what volume can the tubular bowl centrifugation be scaled?
Yeah, we've got a large system that's suitable for bioreactors 2,000 liters and up. It comes down to the density, the application, a few other things, but that's what we're currently, or that's how it's currently sized right now, 2K bioreactor.
All right, one more quick question. A few slides back, you had spoken about primary clarification. How was the viral recovery determined?
Yeah, the viral recovery theoretical maximum. So benchtop centrifuge pelleted out. That is, many hold that to be the theoretical maximum yield of your viral product that you could have. And so we judge a loss or a yield loss based off of that baseline. And so our tubular bowl centrifuge was compared to that. And we only saw about a 3% yield loss. And what we hear from other customers is that for that particular step with some of the other available technologies, they can end up losing some product in that step.
Thanks, Dan. Great presentation. That was really well done. So Dan Nelson from Car Biosystems, thank you for being with us today.